Right now, somewhere out in the universe, there is a star shining brilliantly in the night sky.
Yeah, probably a lot of them.
Well, sure, but I'm talking about one specific kind of star, because this one, it's a complete lie.
Ah, right.
If you could, like, somehow strip away its glowing outer shell, you wouldn't find this roaring engine of nuclear fusion holding it together against the crush of its own massive gravity.
No, you definitely would not.
You'd find a black hole just sitting directly in the center, quietly eating the star from the inside out.
Welcome to the deep dive, everyone.
Thanks for having me. I'm really excited to get into this one.
So, we're constantly told that the death of a massive star is, well, it's the ultimate cosmic spectacle, right?
Oh, absolutely. The standard narrative is always that when a giant star reaches the end of its line, it goes out in this absolutely blinding supernova.
Right, like forging heavy elements, seeding the galaxy, leaving behind a neutron star or a singularity.
Exactly. It's supposed to be loud. It's supposed to be completely unmissable. But today, we're doing a deep dive into Chapter 7 of The Living Grave, Stars with Hearts of Darkness, and honestly, the research here outlines a phenomenon that is deeply unsettling.
Unsettling is probably the best word for it, yeah.
Because it shatters that binary narrative of star is alive versus star explodes. We are talking about the concept of a living grave.
Right, which is just a fascinating scenario.
It's a scenario where a massive star forms a singularity right in its core, but, and this is the wild part, the universe outside doesn't know it yet.
Yeah, the star just keeps radiating.
Okay.
It maintains its shape. It essentially keeps up the illusion of life while this invisible monster gnaws away at its insides.
Okay, let's unpack this, because for you listening, I know this sounds completely counterintuitive.
It definitely breaks the standard model of stellar evolution that we all rely on.
Hmm.
Usually, the core exhausts its fuel, gravity wins, and the core collapses.
And then the outer layers fall in, right?
Right, they fall in, they hit that incredibly dense nuclear material, and they bounce. That bounce creates an outward shock wave.
Driven by like a massive burst of neutrinos or something?
Exactly, and that completely obliterates the star. The transition is violent, it's binary, you're alive, and then boom, you're a dead corpse.
So how do you hollow out a star without the surface collapsing instantly? I mean, why doesn't it just explode like a normal core collapse supernova?
Well, it is the absolute definition of a cosmic paradox.
Yeah.
You have an object of infinite density, right?
Right.
Where the escape velocity exceeds the speed of light, and it's sitting exactly in the cavity where the star's outward pressure engine used to be.
The fusion is just gone.
Gone. The structural support is gone. And yet, the exterior carries on as if absolutely nothing has happened.
But we should probably ground this immediately for the folks listening.
Oh, definitely. We're talking about a fiercely unstable temporary phase here.
Yeah, this isn't like a permanent new class of star floating out there forever.
No. It's a moment of cosmic lag.
Mm.
And the mechanics of how this plays out, whether this illusion lasts for an hour, a few months, or, several years, that depends entirely on the size of the host star.
Which is what we're going to get into. But before we walk through this cosmic graveyard, we have to understand the physical insanity required for this to even happen.
The necessary madness, basically.
Exactly. Because to pull off this illusion, the physics have to align in a way that almost defies logic. We're talking about suppressing the most violent, energetic release in the universe.
Right. To understand the illusion, you have to understand the suppression. The source material outlines 4 incredibly strict, almost impossible physical conditions.
And they all have to be met simultaneously, right?
Simultaneously, yes. If even one of these conditions is slightly off, the illusion is completely shattered, the shockwave forms, and you just get a standard messy supernova.
Okay, let's go through them. Condition number 1.
The first required condition is perfect symmetry in the collapse.
Which, I mean, if you look at the interior of any massive star, is practically an oxymoron. Perfect symmetry doesn't exist in stellar physics.
No, it really doesn't. Stars are violently chaotic environments.
They're just roiling balls of plasma.
Exactly. You have these massive convection zones churning billions of tons of matter. You have differential rotation.
Wait, differential rotation? That means different parts spin at different speeds.
Right. The equator of the star might spin at a totally different rate than the poles. Plus, you have these incredibly complex, twisting magnetic fields.
So the core is a total mess right before it dies.
It is boiling. But for a living grave to form, the collapse of that iron core into a singularity must be as smooth as a glass marble falling through a vacuum.
Because if it isn't smooth, you get a shock wave.
Precisely. Think about the conservation of angular momentum. like an ice skater pulling their arms in.
Right, they spin faster.
Right. If the star's core is rotating rapidly when it collapses, that rotation accelerates as it shrinks. And that rapid spin flattens the collapsing matter into a disk.
Oh, and that causes problems.
Huge problems. It can generate relativistic jets that shoot out from the poles. Those jets will immediately slam into the upper layers of the star.
Creating a huge shock wave.
Exactly. A massive acoustic and thermal shock.
Yeah.
The moment you have a shock wave propagating outward, the star is blown apart. The illusion is over.
It's like a colossal magic trick. I'm picturing, pulling a tablecloth out from under a fully set banquet table.
That's a great way to look at it.
But the table is the size of a solar system. And it's covered in millions of tons of incredibly volatile crystal and china.
And you have to pull that cloth so perfectly, with such absolutely flawless uniform tension, that not a single glass even vibrates.
That is just nuts. Okay, so that's condition 1, perfect symmetry. What's number 2?
Not only do you have to pull the tablecloth perfectly, you have to deal with the sheer volume of what is falling into the newly formed black hole.
The food for the monster.
Right. This brings us to the second mandatory condition, what astrophysicists refer to as the hypercritical trap.
Okay, because normally when matter falls into a black hole's gravity well, it forms an accretion disk, right?
Yes. It speeds up, experiences intense friction, and gets unimaginably hot. It generates a ton of radiation.
Mostly X-rays and gamma rays.
Primarily, yes. And that radiation exerts an outward physical force known as radiation pressure. Normally, that blows the surrounding matter away.
So the light physically pushes the gas?
Exactly. It acts as a strict limit on how fast a black hole can eat. We call it the Eddington limit.
So if a black hole tries to eat too fast, it basically chokes.
Right. If it consumes matter too quickly, the friction generates so much light that the light pushes the remaining food away.
Which would completely ruin our magic trick.
Totally ruin it.
Because if the core collapses and suddenly a massive burst of outward radiation hits the stellar envelope, the star is going to, expand or explode?
Exactly. It would brighten immediately and blow apart. So to prevent that, the accretion rate must blow past that Eddington limit by a factor of thousands.
Or even millions, according to the book.
Yes. The matter must be cascading inward so unbelievably fast. We're talking hundreds of solar masses per year.
Just a waterfall of plasma.
Right. And the density of that infalling material has to completely overwhelm the outgoing radiation.
So the light is trying to get out, but the matter falling in is too thick.
The photons are generated by the friction. They try to travel outward, but they are constantly scattering off the incredibly dense inward-rushing electrons.
Wow. So the light gets trapped in the current. It's physically dragged back down across the event horizon by the sheer mass of the matter falling in with it.
It's a phenomenon called advection-dominated accretion.
Advection.
Yeah. The radiation never makes it out of the core region to tell the rest of the star what is happening. The black hole is gorging itself so aggressively that it swallows the light of its own meal.
That is such a chilling concept. The darkness isn't just an absence of light, it's gravity actively overpowering the outward momentum of radiation.
It's nature brute forcing the problem.
Okay, so we have flawless symmetry, and we have this hypercritical trap dragging light backward. What's the third condition for this impossible scenario?
The research calls it a compact seed.
A compact seed, meaning the core has to already be small?
Crucially small, yes. This is vital for maintaining the structural integrity of the layers immediately surrounding the core.
Because you want the event horizon to form without violently shifting the gravity of the star, right?
Exactly. To do that, the pre-collapse core needs to be extremely dense and compact already. We're talking about a core that is essentially teetering on the absolute edge of the Tolman-Oppenheimer-Volkoff limit.
Okay, wait, the Tolman-Oppenheimer-Volkoff limit?
Right, it's the maximum mass a degenerate neutron core can have before gravity overwhelms the strong nuclear force.
Oh, so before neutron degeneracy pressure just fails completely.
Yes.
So the core is already pre-shrunk. It's just waiting to tip over the edge.
Exactly. It's not this massive diffuse cloud of gas suddenly compressing. It's a tiny, ultra-dense sphere of iron or deuteronium.
And it just quietly blinks out of our observable universe.
Pretty much. It becomes a singularity occupying essentially the exact same gravitational footprint.
So the layers above it don't even feel a change in the gravity. The mass is still there. The pole is identical in that critical millisecond.
Exactly. The inner layers of the onion don't violently collapse inward right away.
Yeah.
They just sort of hang there for a moment.
Unaware that the floor has given way.
Exactly.
Man. But, okay, this brings me to the fourth condition. And this is where I really need to push back on the physics here.
Go for it.
Because this seems to contradict the fundamental mechanics of core collapse. The fourth requirement is the silence of neutrinos.
Ah, yes.
The tricky one.
Because anyone who follows astrophysics knows that neutrinos are the ultimate culprits in a supernova.
They absolutely are.
When protons and electrons are crushed together to form neutrons in that collapsing core, they release an unfathomable flood of neutrinos.
Right. And usually these ghost particles pass through ordinary matter without interacting at all. Billions are passing through you right now. Yeah. But the core of a dying star is so dense that it actually becomes opaque to neutrinos. They slam into the infalling matter, transfer their energy, and blast the star apart.
That is the standard mechanism, yes.
So how on earth do you make a tidal wave of nuclear particles silent? How does that even work?
It is the most precarious part of the entire mechanism. And your pushback is completely justified. You are relying on microscopic particle physics to dictate the fate of a macroscopic giant.
Right, because that neutrino flux carries away, 99% of the gravitational binding energy of the star?
It does. It is an apocalyptic amount of energy.
Right.
And in a living grave scenario, those neutrinos are still produced. The physics of electron capture doesn't just stop.
So they're still flooding outward. How do they not trigger the shock wave?
It comes down to the precise density gradient, the exact architecture of the stellar layers immediately surrounding the collapsing core.
What do you mean by density gradient?
Well, for the neutrinos to be silent, the star's interior must lack the specific density cliffs, the sudden changes in density, that usually cause neutrinos to deposit their energy all at once.
Oh, so instead of hitting a wall, they
They still interact via the weak nuclear force. They still scatter, but they deposit their energy uniformly, smoothly across a vast region of the star's interior.
rather than slamming into a dense wall of infalling matter and sparking a sudden shock.
Exactly. It's less of a wall of energy hitting a brick wall and more like a gentle, diffuse heating over a massive volume.
Okay, so they might puff up the inner layers slightly, alter the thermal profile?
Right, but they failed to break the gravitational binding energy of the star as a whole. They slip out, carrying the energy away without triggering the supersonic shockwave.
I mean, the odds of that density gradient being perfectly tuned, combined with zero rotation, perfect symmetry, and a compact core.
It's a lot to ask of nature, definitely.
Do these four conditions actually ever align in the real universe, or is this just, chalk on a blackboard?
Well, what's fascinating here is that, according to the most rigorous supercomputer simulations we have, yes, they do align.
Wait, really?
Really, but only under the most extreme specific parameters. You need highly massive, incredibly slow rotating stars.
And usually with very low metallicity, right?
Yes, meaning they are composed almost entirely of hydrogen and helium without the heavier elements that typically drive strong, chaotic stellar winds in rotation.
So it is an absolute knife-edge balance of thermodynamics, quantum mechanics, and general relativity.
It is. But if the universe perfectly threads that needle, for a brief window of time, a living star becomes a living grave.
Okay. So we've established the rules of entry. We know the physical insanity required to set the stage.
The stage is set.
Let's look at what happens when this perfectly threaded needle strikes a star that we are actually somewhat familiar with. Let's apply this curse to a red supergiant.
Right. This is what astrophysicists would consider the small giant scenario in the context of living graves.
Small giant. That's an oxymoron if I've ever heard one.
Well, we're looking at massive stars, but on the lower end of the extreme scale, roughly 15 to 25 times the mass of our sun.
Okay, I just want to pause for you listening to make sure we really visualize the scale of a red supergiant.
Oh, the scale's mind-boggling.
Because human brains simply aren't built to comprehend these dimensions naturally. We are talking about a diffuse, crimson balloon so staggeringly massive that if you dropped it right where our sun is,
Its outer surface would extend beyond the orbit of Jupiter.
it would entirely swallow Mercury, Venus, Earth, Mars, the entire asteroid belt, and Jupiter.
Just a vast, tenuous cloud of glowing gas.
Layered inside like an onion, right?
Exactly like an onion. You have the lighter elements fusing on the outer shells.
Yeah.
And as you move down, you go through carbon, neon, oxygen, silicon, until you hit the absolute center.
The iron heart.
And that iron heart is the mechanism of doom.
Because iron is the ash of the stellar fusion engine.
Exactly. Fusing iron requires more energy than it releases. It's an endothermic reaction.
So the core stops producing the outward radiation pressure needed to support the gravity of that Jupiter orbit-sized envelope.
The iron simply builds up, It accumulates mass until it crosses that critical Chandrasekhar limit, and it just gives way.
But because our four impossible conditions are perfectly met, it is an eerily silent failure.
Right.
The research says that in less than a second, the inner two solar masses of that iron core, a mass twice that of our entire sun, simply vanish.
They collapse down into a singularity, a black hole that is, wait for it, just 6 kilometers across.
6 kilometers.
The Schwarzschild radius for a black hole of that mass is roughly 3.5 miles.
You have a singularity the size of a small town.
Sitting in the direct center of a star that spans nearly 1 billion miles across.
It's a marble, a terrifying, infinitely dense, inescapable marble just hovering right in the center of this crimson balloon.
That's the visual, yeah.
So the core is officially gone. The singularity has formed. What happens on the outside? What does an astronomer on Earth see?
For the first month, they see absolutely nothing.
Not a single flicker.
Nothing at all. Because of the vast distance from the core to the surface and the sheer volume of plasma in between, the surface literally does not get the memo.
It just doesn't know it's dead yet.
Right. The dynamical timescale of the outer envelope is completely disconnected from the dynamical timescale of the core.
The dynamical time scale, so the time it takes for gravity and pressure to communicate.
Exactly. So the photosphere, that outer shell of the star that actually emits the photons reaching our telescopes, it just continues its serene 3,500 degrees Celsius glow.
It's just casually bubbling away.
Bubbling is a good word. The convection cells on the surface of a red supergiant are colossal.
Like granules of hot, upwelling gas.
Granules that are individually the size of stars. Those cells continue to churn, driven by the residual heat trapped in that massive envelope.
So if we pointed our most advanced observatories at this star during that first month,
Every spectral line, every luminosity measurement would classify it as a perfectly normal, healthy, aging red supergiant.
here's where it gets really interesting for me. I try to picture it like wrapping a massive, incredibly thick wool blanket around a firework.
I like that analogy.
When the firework goes off inside, the blanket is so tremendously thick and dense that for a solid moment, you don't hear a sound and you don't see a flash.
Right, the outside of the blanket looks exactly the same. The illusion is flawless.
But the firework is still burning inside the blanket. The black hole is not dormant.
No, it has begun to feed.
Right, because once the outward pressure of the core fusion is gone, gravity is the only force left. The inner layers of that onion, the silicon, the oxygen, they've lost their floor.
They do. And they begin to drift inward. Not in a sudden catastrophic free fall from the surface, but starting from the inside out.
Like a sinkhole opening up.
Exactly. The layers immediately surrounding the black hole fall into the gravitational well. But because there is always some minuscule residual angular momentum, they don't fall straight in.
They swirl.
They swirl, forming a dense accretion disk just outside that 6-kilometer event horizon.
And as they swirl, the friction between the particles of plasma in that disk becomes unimaginably intense.
You're talking about temperatures skyrocketing into the billions of degrees. The gravitational potential energy of the infalling matter is converted into thermal energy and radiation.
So the accretion disk begins to blaze with high-energy X-rays.
Glazing, yes.
But wait, earlier we talked about the hypercritical trap dragging the light backward. Advection, right?
Yeah.
Does that not apply here?
Oh, it does. Which is precisely why the star doesn't instantly explode. Much of the radiation is trapped by that infalling deluge.
Okay, good.
But a red supergiant's envelope is vast, and eventually the sheer volume of X-rays generated by the accretion disk begins to leak outward into the surrounding stellar material.
So the X-rays are hitting the inside of the wool blanket.
Yes, and X-rays carry an immense amount of energy. When they slam into the dense, opaque hydrogen and helium of the star's inner envelope, they are absorbed.
They thermalize.
They thermalize, exactly. They deposit their energy, heating the inner layers of the star from the inside out.
The blanket is essentially catching fire from the inside,
That's exactly what's happening.
which means the illusion has an expiration date.
It does. Over the course of the next 6 to 12 months, the physical reality of the core finally overrides the thermal inertia of the envelope.
The heat builds up too much.
Right. The profoundly heated inner layers begin to exert a massive outward pressure. The envelope begins to rapidly expand and stretch.
So what does the observer finally see after, 6 to 12 months of staring at a normal star?
They see a confusing, deeply underwhelming event.
Underwhelming.
Yeah. The star's surface would suddenly brighten as the thermal wave reaches the photosphere and the envelope expands. but it doesn't reach the terrifying luminosity of a supernova.
It just sort of swells.
It just swells. And then, as the envelope expands and cools, and as the black hole finishes consuming the dense inner layers and basically starves,
The energy source cuts off.
right, it dims. The literature calls it a faint red transient or a failed supernova.
Which honestly must be so incredibly frustrating for an astrophysicist watching it.
Oh, it defies all standard classification. Imagine monitoring this massive 25 solar mass giant, fully expecting the glorious galaxy-bright supernova.
You have all your instruments calibrated for the neutrino burst, the gamma ray flash.
And instead, the star just sort of burps a dull red light, swells up, and fades into the infrared before vanishing completely.
You would be left scratching your head wondering if your telescope was broken. Like, why did this massive star just fizzle out?
But we know the truth of the mechanics. Underneath that confusing dimming, gravity won.
The black hole consumed the heart of the star.
And the swelling envelope was just the death rattle. It leaves behind nothing but a thin, slowly expanding shell of cool gas, and right in the center, a completely silent tomb.
The slow, quiet consumption of a giant.
The red supergiant hid its death for months entirely because of its sheer puffy bulk.
Which naturally raises the next question. If the red supergiant's illusion lasted for months purely because of its massive, thick, insulating envelope, what happens if you strip that envelope away?
Ah, now we're talking about a totally different beast.
Right. What happens to a star that doesn't have that protective layer of wool to hide the monster inside? Let's move away from the puffy giants and look at something much more aggressive. The Wolf-Rayet star.
Yes, the blue behemoth. This is a profoundly different astrophysical environment. We are moving up in the weight class now.
How heavy are we talking?
Looking at stars with an initial mass of roughly 25 to 40 times the mass of our sun.
But physically, dimensionally, they're much, much smaller than the red supergiant, right? They wouldn't swallow Jupiter's orbit.
Nowhere close. In terms of physical radius, a Wolf-Rayet star might only be a few times wider than our sun.
Wow. But it packs 30 times the mass into that space.
Yes. They are incredibly dense and they are blisteringly hot.
Wait, why are they so small if they have so much mass?
Because they have already suffered extreme mass loss. Wolf-Rayet stars are essentially the exposed, naked cores of former giant stars.
A core?
Right. Through incredibly intense radiation-driven stellar winds, they have already blown away their entire outer hydrogen envelope.
The puffy wool blanket is gone.
It's gone. They are stripped down to their denser, much hotter inner layers, mostly helium, carbon, oxygen, and nitrogen.
So you are just looking at the exposed boiling engine of the star.
Precisely. Their surface temperatures are staggering, often exceeding 100,000 degrees Celsius, compared to our sun's, 5,500 degrees.
100,000 degrees. That is insane.
They shine brilliantly in the ultraviolet,
Yeah.
and they are fiercely unstable. They're already losing mass at a ferocious rate through those stellar winds, even before any core collapse happens.
Okay, so let's apply our living grave parameters to the blue behemoth.
Let's do it.
The core runs out of fuel. The iron heart collapses silently with perfect symmetry. The hypercritical trap engages. The 6-kilometer marble forms at the center.
All four conditions met.
Right, but because the star is only a few solar radii across, the dynamical timescale, the time it takes for gravity and pressure waves to communicate across the star, that changes drastically, doesn't it?
Drastically is an understatement. In the red supergiant, the thick envelope bought the illusion an entire month.
Right.
In the Wolf-Rayet star, the exterior remains completely unchanged for only about an hour.
One single hour.
Just 60 minutes. For that 1 hour, if you took a spectrographic reading of the star, the intense stellar wind keeps blowing exactly as it did before.
Everything looks fine.
The light signature that tells us what elements are present still shows the exact same broad emission lines of helium and nitrogen. The photosphere is intact.
But beneath that thin, incredibly hot surface, the black hole is already aggressively feeding on the carbon and oxygen layers.
Yes, the consumption is rapid.
This is where I really have to pause and ask.
Wait.
If the exterior of the star is fundamentally altering in a matter of hours, and as we are about to discuss, it violently blasts high-energy radiation almost immediately, is it really accurate to classify this as a living grave in the same way we talked about the red supergiant?
That's a fair question.
Because with the giant, it was a long, patient deception. The surface was totally oblivious. This sounds less like a ghost quietly haunting a house and more like an immediate, violent panic attack.
It is a totally valid distinction to make, and your question highlights exactly why the specific stellar environment dictates the nature of the phenomenon.
So is it still a living grave?
Taxonomically, yes. It is still classified as a living grave because for that 1 hour, the core is undeniably a singularity, while the surface is still momentarily behaving like a functioning star.
Emitting the exact same spectra.
Right. The paradox exists. But because of the severe lack of insulation, because that massive hydrogen envelope was stripped away thousands of years ago, the intense heat and extreme X-ray energy from the black hole's accretion disk simply cannot be contained or muffled.
The wool blanket is gone. You just set off the firework on a bare table.
Exactly. The thermalization that took months in the red supergiant takes minutes here.
Mm.
The accretion energy escapes the core region incredibly fast. Piercing, high-energy X-rays shoot out, propagating through the incredibly dense but physically thin remaining layers of the star.
So the outside just cooks.
The photosphere literally begins to boil from the inside out.
And the illusion breaks violently.
Completely shatters. Within a single day, the overall luminosity of the star doubles as the internal heat breaches the surface.
And then what?
And within a week, the remaining outer layers of helium and carbon are completely blown off by a fast, incredibly hot, radiation-driven wind.
So if it blows its layers off, does it explode? Like, is it just a supernova after all?
No, and that is a crucial distinction. It doesn't shatter with an explosive acoustic shock wave bouncing off the core.
It isn't a kinetic explosion in the traditional sense.
Exactly. Instead, it transitions into something arguably much more bizarre and extreme. It becomes an ultraluminous X-ray source, or a ULX.
An ultraluminous X-ray source, the research says it outshines 1 million suns in X-rays.
1 million suns, yeah.
That is hard to even visualize.
It is blinding, because the black hole is gorging itself so rapidly on the incredibly dense carbon and oxygen layers, and because the material is falling in so violently without any massive outer envelope to tamp it down or absorb the radiation.
The friction just goes crazy.
The friction in the accretion disk is unbound. It generates an X-ray beacon that cuts through the cosmos, completely dwarfing the star's original ultraviolet output.
But it's a flash in the pan, right? It doesn't sustain that?
No, it burns fiercely, but briefly. Once that thin remaining envelope is depleted, once the black hole has consumed the inner layers, and the intense radiation pressure has blown the rest away into the interstellar medium, the X-ray beacon fades.
How long does that take?
This entire violent transition happens in roughly 1 to 4 weeks.
And then what's left?
What you're left with is a naked black hole, sitting in the dark, perhaps with a tiny, incredibly hot, vanishing accretion disk swirling around it.
Just empty space.
The whole transition from a 100,000-degree living star to a naked singularity is completely over in less than a month.
So we have gone from a deceptive illusion that lasts for months with the massive red supergiant down to an illusion that lasts barely 60 minutes with the compact, intense Wolf-Rayet star.
Right.
It feels like the tighter the star, the faster the universe just pulls the Band-Aid off.
It absolutely does. The physical dimensions dictate the timeline of the deception.
But if we want to find the ultimate masters of this illusion, the stars that can maintain the paradox not for hours and not just for months, but for entire years.
Now we have to look away from the modern universe.
Yes. We have to rewind the clock to the very dawn of the cosmos.
Oh, this is easily my favorite part of the research.
It's the most mind-bending part, for sure.
We are talking about the ancient Leviathans, the population third stars.
The first-generation monsters to ever ignite in the universe.
These are the true, undisputed titans of astrophysics.
Hey.
When we talk about population third stars, we are talking about mass ranges that are almost mythical by modern standards.
Oh, absolutely. We're talking between 100 and 500 solar masses.
500 times the mass of our sun.
Yeah.
A single star. It's staggering.
That scale is almost incomprehensible. Why were they allowed to get so big back then, but we don't see them now?
It is entirely due to their chemical composition. These stars formed roughly a few 100 million years after the Big Bang.
So the universe was basically brand new.
Right. They're made of pure, pristine hydrogen and helium, the raw, unblemished materials left over directly from the birth of the universe.
So they have zero metallicity.
Exactly. Zero metallicity. No carbon, no oxygen, no silicon, no iron. Just the primordial gas.
Because the heavier elements literally didn't exist yet, right? They had to be forged by these very stars dying. These guys are the absolute firstborns.
Precisely. And that lack of heavy elements changes the physics of how they form and operate.
How so?
Well, in the modern universe, heavy elements in a forming star's gas cloud act as a cooling mechanism. And they also create opacity that drives strong stellar winds, pushing gas away and limiting how massive the star can get.
Oh, so the metals sort of choke off the growth.
Right. Without those metals, population third stars just kept accreting mass from their stellar nurseries until they reached these monstrous proportions.
But operating at 500 solar masses means they function on completely different physics than a modern star. The pressure inside must be unimaginable.
It is. Their cores are so incredibly hot and so unfathomably dense that they aren't primarily supported by the thermal pressure of the gas itself, which is how our sun operates.
What are they supported by then?
They're supported almost entirely by radiation pressure.
Okay, let's break that down for the audience, because this specific mechanic is the trigger for their collapse, and it is absolutely wild quantum physics.
It really is.
In a normal star, it's the kinetic heat of fusion pushing out against the crush of gravity, right?
Yes. The light, the actual photons generated by the nuclear fusion, exert a physical push outward as they bounce around trying to escape the star's interior.
Because light has momentum.
Exactly. Light has momentum. In a population third monster, the gravity is so crushing that the core has to burn fiercely at temperatures well over 1 billion degrees just to generate enough photons to physically hold the star's immense weight up.
But then, according to the research, the core gets too hot.
Yes.
It crosses a line.
It reaches a thermodynamic threshold where, and I'm quoting here, photons convert into electron-positron pairs.
Right. This is a devastating quantum phenomenon known as pair instability.
Pair instability.
The core is so hot that the photons, the particles of light themselves, achieve energy levels exceeding 1.022 mega electron volts.
And what happens at that energy level?
At that specific energy threshold, a photon can spontaneously snap out of existence and convert its energy into mass,
Wow.
creating a particle of matter and a particle of antimatter, an electron and a positron.
Pure light is literally turning into solid matter.
It is Einstein's E equals mc squared in direct catastrophic action, energy becoming mass. But here's the fatal structural flaw for the star, right? A photon traveling at the speed of light exerts tremendous outward radiation pressure.
Yes.
But an electron and a positron have mass, meaning they move slower and they exert significantly less pressure.
Exactly. When those high-energy photons start converting into pairs, the outward radiation pressure suddenly vanishes.
It's an endothermic trap. It's like the steel pillars holding up a skyscraper roof just suddenly turned into dust.
That is a perfect analogy. The core loses its structural support instantly. The radiation pressure plummets.
And gravity takes over.
Instantly. And so, instead of slowly building up an iron core that collapses over thousands of years, the entire star, all hundreds of solar masses of it, begins a sudden, direct, catastrophic freefall inward.
The scale of this star is so staggering that the outside layers have absolutely no idea what just happened to the inside.
Not at all.
We established the red supergiant was huge, but a 500 solar mass population 3 star is physically larger than Earth's orbit around the sun?
Yes. And this is where the physics of communication within a stellar body becomes so important.
Right, because news takes time to travel.
Think about how fast light travels in a vacuum. It's the absolute speed limit of the universe.
Right.
Yet for a star of this size, and with the immense density of the plasma, it would take hours, even days, for a photon to scatter its way from the core to the surface.
But physical changes, like the actual structural collapse of the core, they don't propagate at the speed of light.
No, they do not. They propagate at the speed of sound within the stellar medium.
The speed of sound.
Yes, the acoustic waves of the pressure dropping.
Okay, so how fast is the speed of sound in a star?
Now, the speed of sound in a superheated relativistic plasma is incredibly fast by human standards. We're talking thousands of kilometers per second.
That's fast.
But it is absolutely glacial when you are trying to cross a physical distance larger than Earth's orbit.
Oh my God.
It takes a full, uninterrupted year for the acoustic news of the core collapse to travel from the center to the surface of the star.
The star is so astronomically huge that it is literally out of communication with itself. I cannot get over that image.
It is wild to think about.
The core is completely gone. It has literally fallen into a black hole. And the surface layers, millions and millions of miles away, are just happily fusing hydrogen, glowing a brilliant, pristine blue, completely oblivious to the fact that they are already dead.
It is the ultimate ghost of the cosmos. For an entire year, the surface remains completely, totally unchanged.
Wow.
But deep inside, the black hole has formed. and the hypercritical phase has begun on a scale that dwarfs the red supergiant.
And this is where that hypercritical trap we talked about earlier really goes into overdrive, right?
Oh, absolutely.
Because of the sheer mass involved, the matter isn't just trickling in, it's falling into this massive black hole at rates exceeding 1,000 solar masses per year.
It's a literal waterfall of primordial plasma.
And this brings us to a crucial astrophysical concept that defines this event, which we touched on, advection.
Yes, advection.
Because the matter is falling in so unbelievably fast, so thick, and with such overwhelming gravitational acceleration, the immense radiation generated by the friction of the accretion disk doesn't just get trapped.
It actively gets dragged backwards.
Like against its will.
Yes. Think of a massive, raging river flowing toward a sheer waterfall.
Okay.
If a fish is swimming upstream against the current, it represents the light, the photons, trying to escape outward from the black hole.
Right.
But if the river is flowing much, much faster than the fish can possibly swim, the fish gets swept backward over the waterfall anyway.
Even though it's swimming as fast as it can.
Exactly. The light is trapped in the relativistic current of infalling matter, and it is dragged straight across the event horizon and into the singularity.
So absolutely no energy escapes to warn the outer layers. The black hole is just secretly, silently hollowing out the star from the inside.
For months on end, the singularity grows more and more massive, gorging on hundreds of solar masses of pristine hydrogen and helium, and the star above it knows absolutely nothing.
Until finally, the inevitable gravitational change reaches the surface.
Because eventually, the black hole's gravity gets so unimaginably strong, and the inner support is so completely removed, that it begins to dominate even those distant outer layers.
Right, because the envelope of the star, which is still shining, still trying to be a star, finally feels this strange, overwhelming tug.
Yes. The core is a gaping maw now, and the star begins to physically drain inward, like water circling an unfathomably large drain.
And what does that look like to an observer? If we had a telescope powerful enough to watch a population third star die, what would we see?
That's the eerie part. There is no supernova. There is no brilliant galaxy-piercing flash of light to signal the death of a 500 solar mass titan.
So it doesn't explode.
The star simply dims.
It cools down.
As the layers fall inward, the envelope expands slightly, the temperature drops, and its light shifts from that brilliant, pristine blue or white down to a dull, bruised red.
And then, after 1 to 3 years of this incredible balancing act, one day, it is simply gone.
It vanishes from the sky entirely, replaced by a gargantuan silent black hole of perhaps 200 to 400 solar masses.
And maybe like a faint little wisp of gas that was just too far away to get sucked in fast enough?
Maybe, but basically nothing.
It's haunting. The living grave lasted for years, and it left absolutely no corpse behind, no glowing nebula, no shockwave, just a massive absence where a giant used to be.
It is the quietest possible death for the loudest, most massive objects in the early universe.
Okay, so looking at these massive timescales naturally begs a massive question.
I think I know what you're going to ask.
If these ancient leviathans can keep up this act for years, and the modern red supergiants can manage it for months, could nature perfectly balance this?
Could it last forever?
Yeah. Is there a theoretical model where a star could host a black hole at its core indefinitely? Could a living grave be a permanent state of stellar evolution?
It's a beautiful thought, and theoretically, astrophysicists have tried to model it.
Because we want to find these stable, exotic stellar objects.
There is a strong desire to find them, yes. But the answer, grounded strictly in the physics and thermodynamics we actually observe in the universe, is a definitive no.
So what does this all mean? Why can't it last? If the envelope is big enough, why can't it just sit there?
If we connect this to the bigger picture, it comes down to a fundamental, insurmountable incompatibility between two diametrically opposed cosmic engines.
Opposed cosmic engines.
Right. A normal star is an engine of nuclear fusion. Its entire purpose, physically speaking, its defining characteristic, is to provide outward pressure.
Right. It converts mass into energy to push outward against its own tremendous weight to maintain hydrostatic equilibrium.
Exactly. It's a balancing act. Gravity pulls in, fusion pushes out.
But a black hole is different.
A black hole is an engine of pure, unadulterated gravity. It provides absolutely no outward force. It only pulls.
So they just fundamentally disagree on what to do with matter.
You cannot have a permanent equilibrium when the core of the object is demanding that everything fall inward, and the outer layers require a constant outward push to survive against their own mass.
But wait, couldn't the heat from the accretion disk, The friction of the material swirling and falling into the black hole? Couldn't that act like a substitute for fusion?
That's a good thought.
Couldn't that accretion energy push the star outward and hold the envelope up?
That is the crux of the problem, and where the physics truly break down. Yes, accretion generates immense energy.
Right.
In fact, accretion onto a black hole is one of the most efficient energy conversion processes in the universe, far more efficient than hydrogen fusion.
So why doesn't it work?
Because that energy is fundamentally destructive.
Yeah.
To maintain a permanent living grave, you have to overcome 3 insurmountable hurdles: pressure, temperature, and time.
Okay, let's look at pressure first.
The accretion energy is incredibly chaotic. It doesn't push evenly and smoothly in all directions like a spherical fusion core.
It's
Very messy. It blasts out in highly erratic, high-energy jets and bursts that literally tear the stellar envelope apart from the inside, rather than gently supporting it.
It's too violent to act as a pillar. Okay, and the second hurdle, the temperature.
The temperature of an active accretion disk around a black hole completely dwarfs anything a nuclear fusion core can produce.
We said billions of degrees earlier.
Hundreds of billions of degrees. That kind of profound heat simply cannot be contained indefinitely by a stellar envelope, no matter how thick.
Because the entropy is too high.
Exactly. The heat will inevitably leak out, inflate the outer layers beyond their gravitational binding energy, and eventually blow them completely off into the interstellar medium.
Much like we saw with the rapid death of the Wolf-Rayet star.
Precisely.
And the third hurdle, time.
Time is the ultimate enemy of this paradox. Gravity is relentless, and it is perfectly efficient.
It never stops.
Even in the absolute best-case scenario, our gigantic population 3 star. With its massive envelope, its perfectly symmetrical collapse, and its advection-dominated accretion dragging the light backward.
Right, the best case.
Even then, the amount of matter available to act as a buffer is finite. The freefall time, the physical time it takes for gravity to pull all that mass inward, has a strict mathematical limit based on the star's density.
It just runs out of food.
Eventually, the black hole eats everything, or the intense chaotic heat blows whatever's left away. Gravity always wins in the end.
So there's no stable version of this. The research mentions that the only way to make a living grave permanent in a mathematical model is to invent entirely speculative physics.
Basically, yeah.
Like hypothesizing a primordial black hole that formed right after the Big Bang that is so incredibly tiny, maybe the mass of an asteroid, that it barely eats anything, so it doesn't produce destructive radiation and it just floats inside a star.
Right. Or you have to invent some exotic, repulsive force that doesn't actually exist in our current understanding of general relativity.
So it's basically sci-fi at that point.
Exactly. We can play with the math in theoretical models and create dark stars on paper, but in the real universe, the physical universe governed by the laws of thermodynamics and relativity that we inhabit, the long grave is strictly a transient wonder.
It is a moment of cosmic lag.
It is simply a star that has died, its heart replaced by a singularity, but it hasn't yet managed to tell its outer layers the news.
Wow. Okay, we have covered a truly massive amount of ground today.
We definitely have.
We started with the sheer physical insanity required to even make this illusion possible. The perfect, frictionless symmetry of the collapse, the hypercritical trap pulling light itself backwards over the event horizon.
The compact seed?
The compact seed, yes, and the precarious, delicate silence of neutrinos.
A lot of hurdles.
And then we watched a colossal red supergiant hide a 6-kilometer singularity in its heart for months, completely muffled like a firework in a thick wool blanket. We saw a naked Wolf-Rayet star panic and violently shed its layers in a matter of hours, blazing with blinding, ultra-luminous X-rays as the illusion immediately shattered.
A very dramatic death.
And finally, we traveled all the way back to the dawn of the universe to witness the ancient Leviathans, populations of the third, monsters larger than Earth's orbit, slowly and silently swallowing themselves whole over the course of years.
Out of communication with their own surfaces.
Leaving absolutely nothing but an empty, dark space behind.
It is a remarkable, sobering journey through the extremes of stellar evolution. And it deeply challenges so much of what we inherently assume about how the universe operates.
It really does. The core takeaway for me, and I hope for you listening, is that the universe is so much stranger and so much more deceptive than our intuition allows.
Absolutely.
We expect death, especially on a macroscopic cosmic scale, to be loud. We expect the brilliant supernova, the blinding flash, the massive kinetic bang.
You want the fireworks.
But nature has carved out this tiny, precarious loophole in the laws of physics. for a quieter, much more unsettling kind of death. A patient, silent, creeping dark that can literally wear a living, shining star as a mask.
And that leaves us with a truly profound reflection, something grounded entirely in the hard physics we've unpacked today.
Yeah.
We look up at the night sky, and we inherently trust the light reaching our eyes. We see a star shining, and we take that light as absolute proof of what is real, what is solid, and what is alive right now in the cosmos.
Right.
But knowing what we know now, knowing that gravity can absolutely outpace light, knowing that acoustic shock waves move slower than the speed of light, and that a massive star can shine brilliantly for years, while internally it is completely hollowed out by a singularity.
It forces you to wonder.
Exactly. How much of that luminous, sparkling universe that comforts us every night is actually just a lingering ghost? A brilliant, perfectly preserved mask, hiding an already empty, silent grave.
Man, that is something to think about next time you look up. Thanks for joining us for this deep dive.